Let's jump into lesson 2 of chapter 2. The big theme today is going to be the concept of differentiability. Differentiability relates to derivatives. Just like limits connected us to the idea of continuity, the idea of a derivative connects us to the idea of differentiability. So for a function to be continuous is one thing, for it to be differentiable is another. So we'll talk about what it means to be derivative, to be differentiable, how to do one-sided derivatives, the idea of the derivative failing to exist, differentiability, how it's connected, differentiability and continuity are connected to each other, and then looking at some graphs and how those are related. So all of this building together with the idea of a tangent line. So the idea of differentiability goes back to the idea of limits. And just like in limits, we had to check one-sided limits. We do the same thing for derivatives. So one-sided limits, we checked the limit approaching a from the left of f of x. And we compared that to the limit as x approaches a from the right. And we had to establish whether or not those two things were equal or not. And if they were equal, then we also had to check the closed value at f of a itself and to see if that was equal. So three things all needed to be equal when we checked our one-sided limits. In a same vein, we check one-sided derivatives. And so from the left, we would check the value of f prime. And from the right, we would check the value of f prime. In other words, we're checking the value of the tangent slope on either side of that point. And then we want to see, are those two things equal or not? Now, there isn't a third piece to checking derivatives. There's only left and right. Is the tangent slope the same on the left of the point and the right of the point? The definition, and this is based on Newton's definition, the a plus h definition. We have a right-hand derivative that's approaching 0 from the left. We have a left-hand derivative approaching 0 from the right. And these two things, if they were equal to each other, then we say the function is differentiable on a closed interval if these two left and right-hand derivatives are equal to each other. So let's check the following piecewise function. So first we want to check the left-hand limit. So the limit as x approaches 0 from the left, and we'll be using negative x. And we plug in 0 from the left, we get negative 0 to the left. When we check the limit to the right, we'll be using the positive x, and so we'll get 0 plus. Now, do we compare these two things? Well, let's look back at the first one. What is negative 0 to the left? Well, that's a double negative. 0 to the left is negative, and the negative in front of it is also negative, and so this is 0 plus. And so those two things are equal to each other. So then we move on to what f of 0 is. And f of 0, using the inequality there, is equal to 0. So we say this function is continuous. So then we can move on to checking its derivative. So now we want the limit as x approaches 0 from the left of y prime. When I'm looking at 0 to the left, I'm looking here, and I want, this is not a curve, this is a straight line. This is a straight line of slope -1. And so the answer to the derivative, which is the value of the slope, is -1. Then we check the right side. And when I check the right side, I'll be using x and it has a slope value of +1. So the left-hand derivative is one value, the tangent slope on the left, and the tangent slope on the right is 1. These are not equal to each other. And so this is an example of where the one-side derivatives don't meet each other. So let's look at visually what that is. That forms a corner. So negative x on one side, positive x on the other forms the absolute value. There is a corner here. So although it is continuous, this is non-differentiable. Okay, continuous, yes. Differentiable, no. Because of the corner. The corner is where the slope on the left side meets the slope on the right side, and they're not equal to each other. So this is continuous but not differentiable, and this is going to happen at a corner. So this is one way at any corner where f prime of a might not exist. So when this happens, when the original limits and f of a all equal each other, but the derivatives do not equal each other, we call this non-differentiability. So show that this function is not differentiable. So you've got the 5 things to check now. You have the limit as x approaches 0 from the left of f of x. You have the limit as x approaches 0 from the right of f of x. And then you have f of 0 itself. Once you've established those things, then you will have the limit as x approaches 0 from the left of f prime, and the limit as x approaches 0 from the right of f prime. All right, so let's go back to the original limit. I'll be using x cubed, and so this would be 0 to the left cubed, which is still 0 to the left. For the right limit, I'll have 4 times 0 plus, which is 0 plus. So those two things are both approaching 0. And f of 0 is 0 cubed exactly. So we say that this is continuous. Now let's go on to check our derivatives. For the cubic, it is a curve. So we'll need to use a limit definition to figure out the value of the tangent slope on that curve. It is a polynomial, x cubed, so newtons would be the best. So we'll have the limit as x approaches 0 from the left of the limit as h approaches 0 of x plus h quantity cubed minus x cubed over h. Now I've done this, and we've done this enough times now, so I'm going to skip all the FOIL and all the expanding and all the reducing, and I'm just going to go to the fact that that will turn out to be 3x squared. I still have my limit as x approaches 0 from the left on the outside. And so then I'm going to plug in 3 times 0 from the left squared. That would be 3 times 0 plus. But either way, that turns out to be 0. Now let's check the limit on the right. Now the limit on the right is 4x. That's not a curve, that's a straight line. That straight line has a slope of 4, which is a constant, and so the answer is 4. Since the left-hand derivative and the right-hand derivative did not match each other, this is a not differentiable function. So we would summarize it with a good statement. Since the limit as x approached 0 from the left of f prime of x did not equal the limit as x approaches from the right of f prime of x, I'm going to run out of room, but since that is true, then f of x is not differentiable at x equals 0. Okay, so that's a summary conclusion statement. If it says justify your answer or explain your answer or prove or something like that. Again, this is a corner. Right? The curve meeting that straight line formed a corner. So it's always going to be not differentiable there, but to show it, you go through the steps of the 5 different steps. Here's another example of an extreme corner, which we call a cusp. A cusp is where 2 curves meet each other. So a corner would be 2 straight lines meeting each other or a straight line meeting a curve. And when we have 2 curves meeting each other, that is called a cusp. And it is where the slope on the left is approaching negative infinity, but the slope on the right is approaching positive infinity, and that forms a cusp. And so you say this: the limit as x approaches 0 of f prime will be approaching negative infinity, but the limit as x approached 0 from the right of the derivative would be approaching positive infinity. And so those 2 things are not equal, and we have a cusp. So this is another way that the derivative fails to exist. Another place is something called a vertical tangent. This happens on a cube root function, actually any odd root function. It could be cube root, fifth root. It also happens on inverse tangent as a graph. But the slope here, approaching from the left, is approaching vertical, so it's approaching positive infinity. And the slope on the right is also approaching positive infinity. And we can't say that 2 infinities are equal to each other. So we say the limit as x approaches 0 from the left of f prime is approaching positive infinity. The limit as x approaches 0 from the right, its slope is also positive infinity. And those 2 infinities are not equal to each other. You can't say that any one infinity is equal to another infinity. And so therefore, this is non-differentiable, a sample of a vertical tangent. So most of the functions we'll work with will be differentiable. The ones that aren't will have either a corner, a cusp, a vertical tangent, or a point of discontinuity. If you see any one of those 4 things, then it's automatically not going to be differentiable at that spot. A good way to think about differentiable functions is to think about something called locally linear. Okay, locally means a small area, a small section. Linear means it looks like a line. Right? If you're using a graphing calculator to illustrate this, a differentiable curve will look like it completely straightens out. It has no more curve to it. So that's, this is not a proof, but it's a way to explore whether or not you think something is differentiable or not. So let's take a look. Clearly, this is a very curvy function. Is it differentiable? Well, pick any one spot on the function and see if you can make it locally linear. In other words, if you zoom in, will it look like it's going to be straight? So I'm going to pick this section right here, and I'm going to zoom in on it, which is the next figure here. And then I'm going to pick this section, and I'll zoom in on that, which gives me this. And it pretty much is starting to look like a straight line. The farther I zoom in, the straighter the line looks. Okay? If a function does that, it is considered differentiable. So again, that is experimenting with it, doesn't prove anything, but it helps you to think about that. You know, so the absolute value function. If I zoom in here, could I ever make it look like a straight line? And no matter how far I zoom in, the corner is still always going to be there. And so I can never make this look like a straight line because it will always have a corner to it. And so that way it's not differentiable. So the implication is, if it's differentiable, it's also continuous. Those two things go together. Okay, it's like a hand in hand. However, the reverse is not true. Okay, so if f is continuous, it may or may not be differentiable. And you can just think of any examples. Absolute value. It's continuous, but it has a corner, so it's not differentiable. And a cube root graph is continuous, but it has a vertical tangent, so it's not differentiable. Right? But if you are told that a function is differentiable, you know it has to have been continuous. If it's differentiable, it couldn't have had any corners or cusps or vertical tangents or points of discontinuity. And so if you're given the derivative first, you know it's continuous. If you're given continuity first, it may or may not be differentiable. Another good strategy is to be able to understand the relationship of a graph of the original function with its derivative and to think of it in terms of slope. So we're going to practice now plotting a graph and its slope. So here's a function. It is continuous, but it has two corners, which means it's not differentiable. I can draw its derivative, but the derivative won't be continuous itself. I draw the derivative in this way. I look at this section right here, whose domain is from -3 to 1, and it has a constant slope, and the slope there is 1. So I go to my other function, and from -3 to 1, I draw a constant value at 1. But I have open circles because of the corner. The next section of the graph I'm going to look at is this one right here. Its x values go from negative, excuse me, I mislabeled that, it's -1. Its interval is from -1 to 2. And it has a horizontal slope, which means its slope value is 0. And so for that corresponding interval, I'm going to do a slope value of 0. And for my last section here, which goes from 2 to 4, the slope value is consistently -2. So on the corresponding interval from -2 to 4, I am going to draw a slope value with its -2. And so that is creating the derivative graph. And if this is f of x, then this is the graph f prime of x. And every time that there was a corner on f of x, there's correspondingly a jump discontinuity on f prime. So let's go the other way. What if you know what the derivative is, and then can you draw a continuous function that matches that derivative? So we know this section is constant at -1 for a value. So I need to I need to go through 0, 4. And for this interval, for all x is less than 0, I need to draw something that has a constant slope value of -1. And so this graph going off to the left has a slope value of -1. Don't really like how that turned out. I think I'm better off coming this way. So now I just drew something that was linear with a constant value of -1. My other section of the graph has a constant value of +1 on the interval where x is greater than or equal to 0. So now I need to, also still going through the point -4, draw something that has a constant slope value. And so that would go up this way. And so I've just created an absolute value graph that's been moved up 4. If my original problem had been modified and say it was -1/2 and +1/2, then my drawing should still go through the same point, but it should have slopes that correspond. And so a slope of -1/2 would be a slope that looked like this, and a slope of +1/2 would go this way. And so I still created an absolute value graph where each side has its own constant slope, but it's a different slope than the other. Or I could suppose that the left side had a slope value of -1/2 and the right side had a slope of 2. Still going through 0, 4. Okay, this side having a slope of -1/2 and then the other side having a slope of 2. So it's not an absolute value anymore, but it does have a hard corner. And again, you can tell it was going to have a hard corner because there was a discontinuity there, a jump between the derivative. So if you've got a derivative that's got a jump in it, your original graph, your f of x now, would have a hard corner. Or if your original graph has hard corners, then your derivative graph will have jump and gap discontinuities in between. So you should be able to go back and forth between derivatives and original functions, either way, starting with one and going to the other in either direction. All right, we'll talk more about this on Thursday morning. I hope you have a good rest of your Tuesday/Wednesday, and I'll talk to you Thursday morning.